Yeah, thank you. So welcome all of you to Alum at Alma Talk. Uh, and our today's speaker is Ujjal. And I request Professor Chandrasekhar, who has been his PhD guide, to actually introduce Ujjal. Over to you,
Okay.
Chandra.
Yeah. Thanks, Rupesh. Yeah. So it's my great pleasure to introduce Ujjal Kumar Dutta. He joined as a direct PhD student and did an excellent work as part of his PhD thesis, which resulted in quite a few uh, number of publications in the top venues. And the topic he has chosen is also kind of a esoteric topic. Not many students who would like to get into that. This is what is known as the distance metric learning, and that requires a lot of good mathematical background, which he developed on his phone and made significant contributions that are highly theoretically sound in nature. And after completing his PhD, he joined with Mintra, and then subsequently he worked at Dolby, and currently is at Sats Sure company. And all his work after PhD was in areas not related to distance metric learning, but quite a few other topics. And he continues to publish in the top venues after completing his PhD also. And today he's going to give this talk on representation learning with self-supervision, and we'll see from natural scenes and e-commerce to remote sensing, just showing the wide range of applications where all this representation learning based on the self-supervision have. And Ujjal is also a sportsman. He was an athlete, and he received many medals in weightlifting, powerlifting. He may look thin, right? But he did win the medals in this weightlifting and powerlifting, and he was also 4 times strongman at IIT Madras. And for his research work, he also received the IBM Best PhD Thesis Award, in addition to the IIT Madras Institute Research Award. He also received the Mintra AIM High Award. That shows that he accomplished not only in research as well as in other activities as well. Okay, he looks a little serious person, but I think he looks beautiful person when he smiles. Right? I hope he's smiling, and he is married to Rupam. She was an MS student here in our department. Both of them are blessed with a son, and it's my pleasure to introduce Ujjal and invite him to give this talk.
Thank you, sir. Thanks a lot for the kind words, and thanks, Rupesh sir, Hema ma'am, and Chandra sir, for being part of my talk. Even I know it's a little bit off hours, and thanks everyone from the attendee list, like for attending the talk. And so I'll be sharing my screen shortly, but prior to that, I'll be giving you a little bit of background. So like sir has mentioned, right, that I had worked on the problem which was called as distance metric learning back then. Like it was not that much of a popular topic. It was more of a mathematical topic where you were required to find some form of distance metric, which is again parameterized by SPD metrics. Like so, however, with the advent of deep learning, we could actually merge these learning of distance metric along with the neural network parameters in an end-to-end manner. And nowadays, this has become, in fact, a very popular topic, and you can actually call it as something which can be found at the heart of almost entire machine learning. And in fact, whatever deep neural networks learn, right, are inherently representations, and then they induce what we call as a distance metric in the learned space. Uh, so uh, let me move towards my slides. Please let me know if it is visible. Yeah,
Yeah,
Yeah, it is with. Yeah.
yeah.
sure. So, uh, so As and when deep learning had advented, right? So the goal was to learn rich discriminative representations which could help you to further identify objects of interest for your downstream task. However, getting these annotations right, depending on different use cases or applications, was a uh, tedious task, I would say. And in fact, it added a lot of overhead. And that is why since 2020, the self-supervision literature started emerging more in the research community, although it was studied in various forms until then. In fact, my PhD work was also something on unsupervised metric learning, but that is something I have used by using graphs. And again, they have their own scalability issues, and then again, their dependence on some form of clustering approaches on the deep embeddings. But modern approaches, they typically started introducing different kind of pretext task, and they were able to scale really faster. Yeah. And in this journey, I'll be talking about with a focus on self-supervised representation learning, and I'll be talking about the pretext tasks that have been introduced in the literature for natural scene images, and then I would be talking about how we went on to solve some of the fashion e-commerce problems using representation learning, and how they can also be applicable for the remote sensing use cases. Briefly about me, I think has already been mentioned by Chandra sir. So I had done my education from Tejpur University and IIT Madras, and during the course of my PhD, I also got the opportunity to collaborate with Professor Harandi from Monash University. Then I joined Mintra, and then throughout my corporate career, I was also involved in some collaboration opportunities with NUS, MBZUI, and more recently University College London. Uh,
Sorry to disturb Ujjal, but I
yes.
think at least from my side, I'm seeing only the title slide still. Uh, I'm not able to see the next slides.
Oh,
Is
sure,
that the
sure.
case with others?
Can you see now?
No, I think still it's the first slide here.
Oh, let me reshare again.
Yes.
Is it possible to see the other ones?
Yeah, so the slide is now visible.
Huh.
Can you just
Is it?
move to the next one? And
Yeah, I have moved. So can you see
oh,
the
I see.
next?
No, at least I'm not able to see. I'm still seeing the title slide. In fact,
Okay.
I'm seeing the window of the viewer, document viewer.
Okay. What about now? Can you see the about me?
No, it's still the title slide. The window
Okay.
of the like SSLRS survey talk.
Okay. Let me then resort to this one. Uh, okay. Are you able to see it now?
Yeah, the
Can you see this about
yes,
me?
yes, great, wonderful.
Okay. Sure.
Yes,
Yeah. Yeah, so I think I was more or less giving a recap of the problem, and I think you can see now, right? These logos and all that.
yes.
Yeah, sure. So I was mentioning about my educational background from Tezpur University, and then I moved to IIT Madras, where I was also able to collaborate with Dr. Harandi from Monash University. Then I moved on to Mintra, and then where I was also in parallel collaborating with some of the professors from NUS, MBZUI, and more recently University College London. Most of the research that I have worked have somehow emerged from the work that I have done during my PhD, like learning representations uh, that are possibly learned in an unsupervised manner as done during the PhD. Then representation learning in generalized scenarios, like more commonly studied as domain generalization, domain adaptation. In UCL, I, out of interest, also explored physics informed neural networks, like with applications in industrial furnaces. Then I moved to Dolby, where I was working on time series data and 3D computer graphics, and working on a more immersive solutions, which Dolby is a leader of. And more recently, I have joined Satshur as a manager of data science, where I'm leading a group of scientists and engineers, including geospatial experts, who drive some of the problems to bring value to the uh, farming community, infrastructure, and utilities applications. So, but before we move on to the topic, right? Yeah, so, what do you think of when we say the word representation? So, I mean, if we are to represent like these alphabets, so we would possibly have some kind of mental mapping, right, of these different letters. For instance, we know what to group together, like capital B and small b are supposed to be, say, grouped together, while being different to the representation of A, right? So. We are somehow making some kind of internal representation in our brain whenever we are encountering some of the common day-to-day life objects and concepts. And this is also applicable in things, right? For example, if we are seeing the image of a cat, there is a speech signal. Someone has uttered a lot of words, which is consisting of a paragraph. And in fact, everything you that learn, right, in this engineering domain, like whether it's formula or everything can be represented as some kind of representation. When we say representation, more formally, what we try to do is like, irrespective of the domain of the data where it comes from, like its image, text, or speech, we're trying to represent it in some form of numeric representation. Uh, this is a little bit different from what computers are at the end of the day representing things like, which is binary. This is more of a mid-level representation, and typically, like most people would be aware of, it is called as a vector, right? So numeric representations, and based on this numeric representation, we try to learn some kind of function, which is helping us to make more sense of what this object is, right? For example, we could tell that it's a cat or it's a transcript, and maybe if we have a good representation of this paragraph, then we can say, maybe make conclusions. For instance, that Macbeth was guilty. Now, now if I ask you, right, how would you learn to represent these cats for a cat detector? So you would possibly try to see these objects by some form of inherent features, right? For instance, these edges, these ears, these whiskers, right? So this is how we humans are trying to learn from the objects that we encounter and form some kind of representations. But in computer science, in computer vision, so when it came to learning representation, there were two schools of thought. One was that of supervised paradigm, where we would be providing some kind of labels to the objects of interest, like images, and the another one would be the unsupervised. So commonly for image data, like we typically leverage convolutional neural networks, where, as you would be aware of, right, we'll be utilizing different kind of features, kernels, and then hierarchically we will be learning different set of features where, and in the initial layers would be, say, maybe representative of the low dimensional aspects of the entity, and the subsequent layers would be more commonly storing the high level representation of the objects present in the images. However, classically, when we tried to learn or representations in an unsupervised manner, what we typically used to do was like, we use something called as the autoencoders. For example, in the simplistic scenario, given an image, we try to encode it into some kind of latent encoding, and then we try to reconstruct it back and try to minimize the losses, with the hope that maybe this bottleneck layer or the latent encoding could be further used in some kind of downstream task. So at the end of the day, what we are trying to do essentially is, given some set of objects, we are trying to learn some kind of representations where possibly the similar things should be grouped together and dissimilar things should be moved apart. So in this case, so you can see the similarity notion is depicted by the similarity in their color. For example, the similar blue color objects and red color objects should be grouped together while moving away the dissimilar colors, right? But what exactly is similar? If I ask you this question, how would you enforce this notion of similarity? Well, in that case, my answer would be that it depends on the use case. So we can they categorize the same set of students based on the courses they have enrolled, or maybe their gender, or maybe the places where they have come from, right? So based on the notion of the use case, their similarity association could be varying, right? Feel free to interrupt me if you have any questions, and I hope so far it's all good, right?
Yeah, it is going.
Sure. Now let's take it to a even higher level of understanding. Uh, Now, are these representations only applicable in the simplistic neural networks like classification or autoencoder, right? The answer is actually no. So if you look at the broad level computer vision problems, right, like classification, where we have been given an image and we just have to tell what is present here, let's say cat, then object detection or classification and localization, where we not only tell what is present, but we also localize its surroundings by virtue of some kind of bounding box. And in fact, for object detection problem, we can actually draw bounding boxes for each of the objects that are present. And if it were a segmentation task, right, whether it's semantic or instance, we would be requiring to represent image the objects of interest by their specific pixels that they are forming, right? Now, in all of these tasks, what I will be taking the example of detection and segmentation, where we would also be passing an image, and then we have a coordinate, and then there is a region proportional network which tells where these objects are, boxes are, and then we try to learn by virtue of different multitask branches like classification and regression. If you look at this architecture, right, everything is a representation. If you call it as a feature map or it's a flattened vector, doesn't matter. We are inherently trying to learn representation, and the power and the discriminative nature of these representation is actually going to drive your performance of the downstream task, right? So you can see the representation is present everywhere. Now we will be talking more specifically about a very common loss formulation which is present in the representation learning literature. It is called as the triplet loss. For example, if any comic uh, fans are there, right? So they may be recognizing that these two images are of Spider-Man and this is Dr. Octopus, right? So based on their characters, so we can tell that this is a hero, this is a villain, but this is say coming from a 1970s era, or this is a more modern version of Spider-Man. So in this way, what we have done is we are getting a triplet of examples, and we are calling the first one as an anchor, then positive and negative. Uh, it means that the anchor and positive are of the same semantics, that is, they are of the um, similar nature, and we want to group the embeddings together while moving away the embedding of the negative example. So let's say we have used some kind of convolutional neural network, right? And let's assume that it's a supervised scenario. Maybe we have used it ImageNet pre-trained model, right? Because these are RGB images. So in the initial embedding, because the ImageNet pre-trained model has been trained on nature scene images, so this superhero image might actually bring the anchor and negative closer by virtue of the ImageNet pre-trained net. But because we are enforcing that anchor and positive are supposed to be similar, what we try to do is that we try to learn a refined space of these data points where we try to pull the anchor and positive together and push away the negative example by certain margin just to be safe. Now, this is what our end goal is. But in order to formulate is a loss, we typically go for a variation of hinge loss. So basically, what we do is we pass these images by these networks. And let's say you can assume it here, right? Anchor, positive, negative. They all have been passed by the same shared network. Basically, we maintain three copies of the model checkpoints, but with the shared weights. And then we can compute a representation for the anchor, a positive, and the negative, and then we just try to formalize this in terms of the Euclidean squared Euclidean distances. We won't go into the details of it, but just to give you a flavor, right? Like that we have a triplet and we encounter some form of mathematical laws. Now, where are these applicable, right? We know they are applicable in natural scene images and most of the domains that we see, right? Videos, everything. But I'll also be talking about some of the problems that we encounter in the satellite imagery or remote sensing domain. So one problem is called as the LULC, the land use land cover problem. For instance, if you want to understand, right, which parts of India are having barren land, which are having cropland, which are having different types of forest, this you can call it in the image processing domain like a segmentation problem. But how do you learn it, right? There would be representations inherently. But again, challenges the scale and the resolution of the images that we'll be playing with. In that case, for instance, there could be another problem of farm boundary detection. Now, these images look very clean, very good if you are considering them from, this is coming from the Netherlands, right? Or maybe Brazil or something. There, the farm boundaries are very uniform, very well separated. But in India, it doesn't work like that. Even if you go for some kind of state of the art model like segment anything model, right? Recently, SAM2 has also come. They won't work very well. But what we do know is like at the heart of all these kind of problems, there lies some kind of representation learning. And if we can crack it, we may possibly able to generalize better and learn better the UN task that we are having. Likewise, there's even challenging problems of crop classification, like looking at different kind of geographies of the different states of India and districts and sub-districts. What actually happens is farmers go to the banks for loans, right? And there's a lot of money involved. And now, how do the banks decide whether the farmer should be given a particular loan or not, right? So, because it could lead to huge implications, right? Like based on whether the crop is actually able to take the loan and produce the desired amount of yield. So, what we typically do is we monitor from our satellite images different regions of the country, and we try to get insights from the historical yields that each farmer is able to produce. For that, we not only have to look at the district or state, but also at the farm level. And within the farm level, we also have to do even a challenging problem of crop classification, like what crop is being grown. And it is very difficult. So this is how something it will look like at the satellite domain. Like, right, it's not something that's very easily solvable by uh, existing models. Likewise, whenever the crops are being harvested, we have to work very closely with the geospatial teams, and you need to understand the agricultural domains, right? Like when you want to solve these geospatial problems using computer vision or machine learning. For instance, right, there is a problem called the sowing progression. So what happens is like whenever the seeds are being sown, typically there would be a peak over time, and this is where the crops are growing, and then there will be a harvest period, and this is something that we can get the information from satellite image, multispectral satellite, and compute what is called as the NDVI metric. Uh, but what happens if there is a cloud cover? There won't be a rising profile here. In fact, there is going to be dip. So what we try to do is we not only rely on multispectral images, but we also rely on SAR data from another satellite called the Sentinel-1. So in that case, how we are merging the information from two modalities by using representation learning helps a lot, right? Because that way we'll be able to make use of complementary data like optical data and SAR data. And uh, and one important thing when we have to consider while dealing with satellite images is that most often satellite images are present in the form of satellite image time series, because these geographic areas they evolve over time, right? There could be variations here, like someone has cut the tree, someone has built a building over there, or anything could happen. So basically each of, and again when we are talking about satellite images, we specifically deal with optical data from Sentinel-2, which is the most closely resembling the data source to that of our RGB images, but they are of multi-band in nature as well. So it's not just 3 channels anymore. It is up to 20 channels where if we are talking about MSI, and if we are going for hyperspectral, so it will can actually be hundreds of continuous bands. And each of these pixels could, in a very simple way, be interpreted as a time series. So you see, right? You when you want to deal with these kind of applications, you have to combine your knowledge of data science, machine learning, time series, computer vision, and see what is most suitable for your use case, right? Now we'll be talking more specifically about a problem called as change detection in remote sensing, which can actually be solved using LiDAR, but it may not be available at inference. So what do? We may have to look at pure imaging based solution. So simply put, you can see that there is a pair of temporal images like from different locations. In A, you can see different locations, and then in B, you can see the same corresponding location at a different instant of time. Now, you can tell that I am just going to be subtracting them and then get a binary mark, but that doesn't work that way in practice. In fact, there could be small pixel level changes that could be happening. In fact, when we speak of high resolution imagery in satellite images, each of the pixel is actually able to represent a spatial area of 10 cross 10 meter. So in satellite imagery, if we are saying that a pixel is representing 30 cross 30, it is of low resolution. On the other hand, if it is of 5 cross 5, so it may be of high resolution. However, for the public, most of the available data is around 10 meter. So how do we tackle this problem, right? Basically, the goal is to detect if some change has happened. So for example, you can see different kind of change. Some buildings might have been built here. So how do we do it? Now, it is good if we can get some kind of ground truth binary mask like this, and then we can train a deep neural network, right? But in fact, there is something that some of the people in the literature have done as well. I won't be talking in very depth about each and every module, but I just want to give you a flavor and of how people have solved these kind of problems. So, at a very high level, let's say this is an image of the geographic area at timestamp t naught, and this is at timestamp t1. So, and we assume that we have a ground truth which tells us whether a pixel has changed or not. So we can actually use a deep neural network here, like based on content. So one approach that this paper has done recently is like they use the cascaded cross attention based difference learning module. So the idea is very simple. Like what they do is they try to learn hierarchical features for each of the time step, and then they try to apply some form of attention between a pair of blocks at each of these corresponding blocks like I, uh, J, like K, like that. So basically, they try to attend the pair of intermediate feature maps, and then they learn a attention matrix. So this is what forms the attention component, and then they do a cascaded learning. Basically, it makes sense to have a cascaded feature learning. Like I mean, they downsample and then upsample and then merge the features from the subsequent blocks of these coordinates so as to learn better representation. So basically, it's a combination of temporal attention and cascaded learning. And that's good from an architectural point of view. Now, if we have to think of the loss that is being used, so we still can use the commonly used losses like focal loss, as you may be aware of that it is better in terms of focusing more on the misclassified examples compared to the standalone cross entropy loss. In fact, it's a variant of cross entropy loss. And at the same time, like I have said in the beginning, right, the triplet loss, which used anchor positive negative. So this contrastive loss is also being used in this method. So where the D can be your ground truth level telling whether the change has happened or not. So whatever these losses are present in normal computer vision literature can also be used in these remote sensing tasks. But all these architecture, all these losses you can use when you have the ground truth, right? But we don't have the luxury of ground truth. I mean, it's a huge data set that you'll be getting in petabytes, and then your clients may not be able to provide you the ground truth. And in fact, we have actually gathered ground truths for many of the use cases. But in remote sensing, things work very differently. It's not that someone is just sitting on the computer and then annotating something. We have to do it on the ground, and uh, people actually go to the agricultural fields and click photographs of the crops that are present. And in that process, what we get is we get very, very noisy ground truths for solving our machine learning model. And that is why the self-supervised feature learning is something that we could actually rely on to solve remote sensing problems also. However, the challenge is to identify the pretext task. And in fact, if we can crack the problem at hand and decide an appropriate pretext task, we can actually lead to the learning of foundation models for our use cases as well. Like you have been seeing and hearing about different kind of foundation models for time series, video, text and video, right? Multimodal learning. So we can do that for remote sensing as well. But how do you learn this pretext task? I think many of you may be aware of it in natural scene images. Like back in 2015 or 16, when unsupervised learning representation learning was not that popular. So what people did was they came up with different kind of heuristics. For example, they proposed that, hey, I have this cat image. Let's uh, blur this thing, right? Or maybe just block this thing. Can the network predict in terms of pixel what is present here? Say if you say aeroplane, then we do this thing here. And similarly, if I give you two crops of the same object, can we tell that if this is present towards the north, west, south, or right is respect to this particular crop? Or if I am applying a different kind of color jitter in my input image, can the model predict the color? So what is actually happening is, in doing so, although we do not have the ground truth class labels, by and this is very commonly called as masking, colorization. I think it is also applicable in other domains like speech and text, in fact. But what happens is like if I ask a human, right, can you tell me what is present here? So they can very easily tell that yeah, there is a cat present here. This is because irrespective of the color, we humans have learned to represent the object that is present here, and we have the same hypothesis and make it as a premise to train our neural networks in an unsupervised manner. So this is what has been done early 2016 or so. Then there were also other pretext tasks, for instance, jigsaw puzzle. Like if I take different crops of this car, shuffle them, can the model come up with the correct permutation and combination of these patches and get what the object is present? However, in 2020, a paper from Hinton's group in Google have proposed what we know as the SimCLR method. It proposed a very simple method. What it does is like, given a mini batch of images, it will pick a random image and apply a pair of augmentation to the same image. Now, theoretically, it makes sense to represent them together, right? Because this is and this part is actually coming from the same object. So we need to pull the embeddings of this pair of patches. And on the other hand, if there is another image from the mini batch, so maybe we can assume that it is of different class from this image and repel its embedding. Now, you can actually tell that this image could be a dog image, right? But if you have to see statistically in a mini batch, very likely and most of the cases, this image would be going to be from another class as that of the dog image. And in fact, when you look at their loss formulation, right, the info NC, what happens is like in the denominator, when you are summing with all the embeddings from these different images, so the majority of the terms are going to overpower the lesser numbered dog images which could possibly be present in the mini bets. And hence, this principle actually works in practice. And in fact, it works really very well and has formed the foundation for most of the representation learning approaches present in almost all of the modalities in literature. And architecture wise is still the same, like you pass it by continent, flatten it, have a MLP, and then yeah, normalize temperature, cross entropy loss. So this is what people uh, have proposed in early 20 and has become very popular. So so far, any questions by any chance, or shall I proceed then, assuming it is a no?
Yeah, I think please continue.
Sure. Yeah. Another form of pretext task which has been proposed is that of the RoadNet back in ICLR 2018. So what they did was like they said that we can try to learn a representation in an unsupervised manner if the what we do is we rotate the image by a certain degree, and now that we know what are the degrees by which you have rotated the image, we use them as the pseudo class labels and teach the model to predict the angle by which an input image has been rotated with. And in doing so also, right, irrespective of the rotation of the subject, we are actually able to tell that it is a bird image presented. So that is also another form of self-supervised representation learning. And then one challenge with SimSLR was it had to use very, very large mini batch sizes, right? Like I said, right, the negatives have to be meaningful and of diverse nature. So they had to train with large number of mini batches. Again, few of the people could afford, and sampling negative examples was a huge pain point for real world applications. So paper came from DeepMind in 2020, called as Bootstrap Your Own Later or BEOL. What did they said that I don't need the negative example, just give me a positive pair. But then the question is like, if you just pull similar things together, what might happen is the model might learn a very, very trivial solution. And it is called as a model collapse, also happens in GANs. And you won't be learning any meaningful representation. To get rid of that, what they did was like they introduced what we call as a encoder and projector network. So basically, the first part is what is called as the encoder, having the shared weights, and they are actually learned in a EMA manner, like exponential moving average, because it is also something analogous to a teacher-student network. Like this is a student which changes fast, and this is a teacher which changes slow and gives pseudo targets to the student network. And then there is another layer after the encoder called as prediction layer. So they simply try to minimize the L2 loss with that. And it works actually because they are also applying a stop gradient. They don't pass the gradients in this network. And there are actually, upon further examination, people realize that there are also batch norm layers here, which are also helping avoid the model collapse problem in this self-supervised learning literature. So these are some of the key architectures. Now, when I was in Myntra, right, we had actually solved a lot of problems that are used to serve our millions of customers in the country. So if you look at the product display page, right, let's say if you search for men's t-shirt, so you can see that different kind of images from men's t-shirt come, and once you click on it you can see different kind of images also. This is something called as the product display page, PDP. It is present in Amazon, Flipkart, and all the other e-commerce. Now you can also see that along with the men's t-shirt, we also recommend similar products that could go with that attire, right? Like similar men's t-shirt, and not only t-shirt, we also try to recommend similar shorts, similar pant, shoes. So you can see that this is again also leveraging representations, like say object detection is there at play, like you do the cropping of the primary article types, and then for each of them you can build a similarity learning model, representation learning model. And this kind of recommendations actually help promote cross sells and thereby increasing your RPO metrics. And right for but whenever we are building solutions, right, we are not only constrained by the clean PDP images that you could see in the platform, right? Many a times users upload comments, reviews, and then they say that, hey, I bought this t-shirt, but it's not fitting me well, or it's not the color I wanted. Or some influencers are also uploading different kind of images. Hey, this is how it looks like on me. So there is so many domains of data that we are actually able to leverage and possibly build better models. Why do we need to build better models, right? We cannot just be relying on the clean PDP images. If you look at the Myntra app, there is also something called as a Myntra Studio, which is like an Instagram feature present in the Myntra, like where influencers would be uploading different kind of images, different kind of videos. And when people are browsing through them, so we also showcase what are the products you could buy, because the end goal is to facilitate more purchases, right? So what could be going similar, what could be going better? So everywhere we have to do these kind of recommendations. Like internally, we used to call like shoppable look, studio, and attribute extraction. And here also, the learnings that we study in the natural scene images, like domain generalization, class incremental learning. The domain generalization is applicable here also. Like it is no longer from the clean PDP images. It could no longer be even having a full post human model. We can get this kind of information by post estimation models, right? Bottom up, top down, open post, and all that. And then what happens is like whenever we are training these models at scale, we cannot be waiting for the ground truth to come in one batch. It is a continuous process. It happens over the years, over the quarters. So what we do is whenever we have say a model, we are building it and then say launching it, right? But as and when there are different kind of annotations that are coming to in subsequent batches, should we retrain everything from scratch again and again? No, right? That's where the learnings from incremental learning or class continual learning that you might be hearing of in the literature are very beneficial. So we have actually used techniques like elastic weight consolidation and served a lot of them. And there is also a my stylist use case which you might have seen in the platform, right? When you are giving an apparel and then it is actually recommending you different kind of apparels that could go with this and complete the whole of the outfit, right? So there we are using different kind of representation learning techniques and Bayesian recommendation systems and so forth. So another problem that I have been a primary owner of, like you can see the more colors features, right? So whenever looking at a particular apparel, we can also see that, hey, I don't like this color, but I do like this design. Can I have a glance at different colors that are present of this article type of the exact MRP brand, everything? So this is called as the color variant problem. So this is where also you can use representation learning, but we actually tried with a supervised model, but then again, the problem of getting annotation was challenging. So what we did was we built a self-supervised learning model here, like again, having different kind of steps like object detection, representation learning, and clustering. And we were able to see that with some amount of misses, we were actually able to improve our recall compared to a supervised model, and also some of the approaches that were present back in literature at that time. However, so this is the architecture that we have used. It is something similar to Moco. Like we have the variant of SimCLR, but we are making use of a large memory queue here so as to facilitate comparison with a large number of negative. But this is where the important part comes into the picture, where we use different kind of uh, horizontal and vertical slicing, and then this was beneficial for different types of data. For example, some of the apparels where you could see these kind of horizontal artifacts present in the apparels, so horizontal slicing was better. And some of the cases here, the vertical slicing was not performing well. So this is just to give you an impression of based on what pretext task you choose, the performance of the model could vary a lot, and you may have to play with a different combination of pretext tasks. Like in this case, along with the self-supervised model, we had tried out different kind of slicing strategies, and the motivation of which came from the person re-identification literature, where using different kind of slices of the input images was proving to be beneficial in improving the recognition performance. And we also observed some interesting conclusions, like now that we have built a model for these color filling tasks, are these also generalizing to other use cases? Can we straightforward use the checkpoints for other use cases? So we found that there was another unrelated product mapping use case, and we just tried to use the checkpoint from the color variance model, and we tried to do an inference on that, and we found it was performing quite comparable to a VIT based dyno checkpoint. And in fact, this is what forms the basis of these foundation models, right? We train them using certain form of pretext task for a certain use case, but we are also able to apply them on different kind of related or unrelated use cases, right? And adapt to the certain new use case more quickly. Now, coming back to our problem of change detection, we were trying to see if there has been a change or not. While contrastive learning that I have talked of or triplet learning losses could be useful, there's also another form of unsupervised learning that you can use. And if you have rightly guessed, like we can draw inspiration from generative adversarial networks. So what they do is they mimic a setup of generator and the discriminator. However, they don't start with the noise to the generation part. Instead, what they do is they provide an image from one time step and another image from another time step, treat one of them as a real and the other one as the fake. And if the discriminator is able to detect or not detect whether it's real or fake, possibly it is learning something, some information inherent to the geospatial location present in the image. Right? So that is what is also another way of learning representations, not necessarily following contrastive learning. This is what they more formally do it, though you can skip it. But now the question is, what is the high level framework of using these self-supervised learning models in practice? There are two steps. First one is the foundational model training, or as we call it as a pre-training step, where we use some kind of self-supervised approach and learn some initial representation. And in the next step, what we try to do is based on a use case, we go for either zero, low, few shot representation learning, which you can call it as a fine-tuning step. However, this is a little bit different from transfer learning, where we actually still utilize a large enough number of samples for fine-tuning this network. On the other hand, zero low will be leveraging very few, like only say 2 to 3 samples per class, right? This is very helpful in practical scenarios where we do not have label data. I mean, these are very popular in the language literature where these things came earlier than the vision community, because they have inherent notion of vocabulary and like using masked word prediction, etc., or next sentence prediction was much helpful in text. But in the vision community, we discovered it later. Now, how do we apply contrastive learning for change detection, right? In self-supervised scenario, a very, in fact, before I move, I would like to tell that most of these pretext tasks that you hear of would sound always almost very counterintuitive and very trivial, but this is the best we can do when we do not have any labels and when the complexity of the real application is very challenging. So what these authors have done is they consider an anchor from a certain geographic location, and then they try to find an anchor from the same location but from a different time step. And another, the negative is sample from a geospatial location which is very far from the anchor. We hope that most of the cases when we are training like this, right? Like I talked about that SimCLR example, right? Anchor negative coming from the same class. Most of the cases here, there is less likely to be change in the same location. And this is actually in a way helpful to learn a self-supervised representation for the satellite imagery. And this is also the same kind of logic has also been applied on one of the older papers, like tile to hack is something that came much earlier than this method, but they also use similar kind of logic, like bringing anchor and positive from somewhat spatially related areas. And then other researchers, what they did was like they tried to have similar kind of augmentation but different kind of architecture. For example, if you recall the Biol architecture, right, where we have a student, a teacher, and then we are only updating one of the network and using contrastive loss. So here also, if we have a set of images, what we are doing is like we are forming different kind of augmentations. Like let's say for this image, one crop is forming the anchor and the nearby crop is forming the anchor positive, and we are repeating it for all of the images. Now, another form of self-supervision that has been used is the geocoding information. Most of the cases we have a latitude and longitude associated with the specific geography. So can we have a image to image pairwise architecture using contrastive laws and at the same time use this latent embedding to perform a geolocation? But that could also possibly guide our network. And the good thing is that we don't need image-based labels here. Now, then we can simply use a pair of images for varying temporally, but are from the same geolocation. These looks very simple, but then people have also moved to more complicated forms of self-supervision. For example, given an input image, we do some kind of color jitter. And these are, by the way, multispectral images, so have much more bands, and hence we cannot use RGB based pre-trained network. We can get their reconstruction, do a color jitter here, and see if we can align the color jitter of the constructed image and the original image. This could form one of our pretext tasks for self-supervised learning in literature in remote sensing, and then we can have a where whatever limited labels we have, and we can have a fine-tuning step, and then do a ensemble here. Like for example, we can pass this network in one branch, this network in one branch, and do a averaging of the final prediction. One noteworthy thing that we typically apply in satellite imagery is like whenever we have multi-band images, we typically, if we want to use a say ImageNet pre-trained model, we just need to select three of the bands out of the multiple. So this is called as false color composite in remote sensing literature. And so this is one way to do. Now, the simple use cases in remote sensing, if you want to just detect what object is present, you can still go ahead with the rotation like pretext task, like we have talked in the case of the bird. Then now I talked about the augmentation at image level. I talked about architecture. We can also do innovations at the end of losses. So what people have done is with the limited levels, we can train a classification loss. We can have a self-supervised loss. Further, we can perform a mix-up on the loss level as well. So what is mix-up? I think many of you be aware of it. So in computer vision, we typically say hey, this image is either going to be cat by its one hot encode factor or it is dog. But in doing so, maybe we are making the model predict in an overconfident manner. But what if we were to confuse it, right? So maybe we can mix the images at the pixel level, a cat and dog, with some probability. And then the network is expected to predict that with 70% accuracy, confidence, maybe it is dog, 30% it is so sorry like 70-30 cat is to dog ratio, right? You can actually formulate this in the form of your ground truth by basically what they do is they sample one image, another image, and then mix them at the image level, and they also mix their corresponding ground truth. So this lambda is sampled from a beta distribution, and in fact this is something that you are not restricted to the image level. I have personally used it at feature level of time series, and this is a very simple and yet very successful way of doing augmentation at when you do not have sufficient information or when you have confusing classes. So there are different form of mixing things like cutout, cut mix, mix up, but mix up is something that is very elegant because of its theoretical formulation. It works very good in practice as well. So the mix-up is actually used typically for augmentation at the image of feature level, but you can also, these authors in the remote sensing context have actually used mix-up loss for the law at the loss level, like how much weightage should I be giving? You can do it using a hyperparameter, but this is basically a little bit variation by using mixing of the different loss components. Now, I talked about the color jitter and of my pretext task at the data level, talked about certain properties of architecture, talked about losses. At inference time also, you can try to improve the performance further. One simple way would be, let's say, to make use of a gap operator, global average pooling. So what you can do is like, let's say now at inference time, whenever you have an image, you just don't pass it by a network. You also apply different form of say rotation, get their corresponding embedding and get their average. This is also likely to boost your performance by certain percentage points. Now, coming to cross-model fusion, right? I told that like there could be cloud cover, there could be inherent challenges associated with different kind of modalities. In satellite imaging, we have three different kind of data sources. One is the multispectral satellite data, which comes from the Sentinel-2 satellites launched by the European Space Agency back in 2017, if I recall correctly. And then there are also something when cloud, this is something that could be seen as a sibling of what we see for RGB images. This will look very similar to what we will be looking RGB domain. However, this is something that is called as optical data, and it is prone to cloud and environmental factors. And that is why synthetic aperture images from the SAR domain, where we focus on the VVVH bands, and that is provided by the Sentinel-1 imagery. At the same time, we also have something called as hyperspectral images, which in theory provide hundreds of bands, but more of a continuous representation of what multispectral, but it is very expensive. It's still not yet as mature as the multispectral use cases, especially for practical scenarios. Theoretically and in the research community, a lot of work has been done here in universities, but for practical use cases, we are still relying on Sentinel-2 and Sentinel-1. So how do we merge these information from different modalities? Without going too much into the details, what I'll try to say is, let's say there is a modality 1, modality 2. At the feature level, you can do some kind of plug and play interaction between them, right? Addition and then passing by different kind of multi-layer perceptron. And what we can come up with is something called as interactive module. There is another thing we can do is called as a self-adversarial module, wherein we again try to do some kind of feature playing and pass these features to a discriminator and see if they are able to distinguish between the original or the uh, recomputed feature, and then we pass it for the subsequent stage of the network. And so this is called as the self-adversarial module. And when you are not having a large label data for certain modality, you can of course go back to your first principles of like label propagation that you have been using in self-supervised learning literature for other domains, right? So these three modules have been used in one of the approaches proposed in literature, where you can see that there are three different modalities like labeled hyperspectral, labeled multispectral, and a large unlabeled multispectral image dataset. And then we apply different kind of adversarial label propagation and interactive learning module. And we try to learn more robust and generalizable representations for satellite imagery. Now we can also, in the same network, apply different kind of pretext task and mix and match of different kind of contrastive learning like rotation, contrastive learning, image in painting. So these are different kind of variations that we can try out in remote sensing literature as well. Now, there's a very key method that also came and that was proposed, and it says that instead of doing at the image level representation by global pooling, what we can do is we can tackle the problem at point level or pixel level as well, where we try to first identify background and foreground, and the points that are aligned spatially, let's say if they are coming from the background, pull them. If they're coming from the foreground, pull them. But if they're coming from the background and foreground, then push them. Similar principle of contrastive learning, but the way they do it is a little bit different and tricky. What they do is they have a pair of images. Again, let's not go into the details of it, but they will be trying different kind of views, and what they do is also they will do a background swapping and again further generate different kind of augmentation. They pass them by different kind of shared architectures, right? Like we told about in the triplet loss. Similar kind of thing is going to be encoder, weight sharing. And then you can see this red, blue color. So these are corresponding to different kind of pixels. And then we again in the final hyperspace we are trying to pull the similar embeddings, push the similar embedding. So you can see all the concept that we have talked about in the early half of this talk being applied to remote sensing in different forms. And specifically this paper, what they did was when they introduced the background swapping was they would identify a common background between a pair of images and use that as a mechanism to swap the background of these images and also further apply different kind of color jitter to make more variations. And there's also a paper by Google Research in 2022 from our Bangalore team only. So they also have utilized this Sentinel-1 and Sentinel-2 as two different forms. And if they are from the same geolocation, then they are trying to apply contrastive loss. And network architectures are quite similar. And you can also additionally utilize different form of information, right, which need not necessarily be restricted to the geolocation or your intuition at the image level. You can actually utilize different kind of human factors also, right, like what do you call, like information of human factor, like what is the population over there, what are the other factors, right, that you can obtain from these government records, etc. And based on that you can form different kind of contrastive pairs, like in addition to pulling pairs which are geographically similar, or maybe seasonal pairs, like same geography but from different seasons. You can also pull images which are having the similar POI information. So I'll be concluding my talk here. So this is my last slide. So the purpose of this talk is to give you the ingredients that you could familiarize yourself in solving not only nature's scene images based problems using SSL, but you could also get a feel of what kind of things have been used in remote sensing, or also maybe in the fashion domain. So one thing we talked about was the temporal attention, cascaded feature fusion that could help in feature learning. Now, if you have the ground truths, or if you have some pseudo level, then this is something that has been proved to be quite powerful. Then pretext task is quite an important choice for SSL, like where we talked about in painting, direction prediction, color, jigsaw, rotation, right? And classically, when people had proposed contrastive learning in 2020, things some of the components that really stood out the test of time were like EMA, exponential moving average, positive pair based methodologies. Most of the new methods are now positive pair based. Memory queue is something that I have found personally very important. Like I had tried SimSiam Biol for one of the fashion e-commerce use cases, but they didn't work quite well. In fact, the more older method based on memory queue was actually performing better, because I was actually able to leverage up to 5,000 distinct negative pairs by forming that memory queue. Then multitask learning, mix up, gap, they are still helpful in different domains. And when it comes to cross-model learning, right, you can apply different form of adversarial interactive learning or label propagation when you do not have enough labels. And we also talked about point level embeddings, contrastive learning with human factors. So as a message, what I would say is like always choose your pretext task based on your use case. You need to think through it, come up with some heuristic, and see what is it that you are going to be using. No one size will ever fit your approaches or all your use cases. And whatever you choose, at the end of the day, you need to validate it empirically, right? So that's all from my end. Like you can feel free to reach out to me at ujjal@satshow.co, and there are always some of the openings in the data science team. In fact, I'd also be hiring in the near future. You can look into this page if that interests you. Yeah, that's all from me.
Thank you.
Thank you very much, Ujjal. Anybody has any questions?
Yeah, I think I covered quite a bit of material. I think it takes
Yeah,
some time to kind of absorb and assimilate. Yeah,
yeah,
it's really nice to see, right, wide range of topics related to this representation learning using the self-supervised methods being covered. Right, it's not a simple review of the literature, right? A thorough understanding of the different techniques in a wide range of applications being understood and then presenting in its own way, right? That's what is really appreciated. I really wish there was much wider participation for this kind of talks. There is so much to get benefited from this kind of talks. I hope the recording of this talk will be seen by larger number of people, right? Not only in the department, maybe from the other places as well, right? Uh, maybe we should have one more talk sometime later. Okay,
yeah.
with the wider
Sure,
participation, right?
we can.
Yeah, I really appreciate what
Mhm.
you have presented, right? Yeah, thank you, Ujjal.
Sure. Yeah. Thanks a lot, everyone, for being patient with me. And yeah,
All right. If there are no questions, then we'll stop here. Thank you, Ujjal.
sure.
And thank you, Chandra, for joining and introducing Ujjal.
It's a pleasure. Yeah.
Thank you, Rupesh sir, for inviting also. Yes, yes.
All right, so we'll stop here. Aditya, you can stop the recording, and thank you everyone for joining late in the day. We will close the session now.
Yeah, do visit us, Ujjal. Maybe an in-person talks can